Our next section of Chapter 11, 11.2, inference about two means, dependent samples. So we're going to, again, look at comparing samples. In this case, they're dependent. Our first objective is to test hypotheses for a population mean from matched pairs data. And remember, matched pairs is dependent data. Statistical inference methods on matched pairs data use the same methods as inference on single population means. So that works in our favor. We're going to do the calculations in a very similar way, except that instead of using one data point, we're going to use the data point of the differences between those two matched pairs of data. To test hypotheses regarding the mean difference of data obtained from a dependent sample, we use the following steps. Provided, and again, this is nothing new, the sample is obtained using a simple random sampling, or the data result from a matched pairs design experiment. The sample data are dependent. Again, that's part of this. And the differences are normally distributed with no outliers, or the sample size n is large, n is greater than or equal to 30 is what we mean by large. Again, this is nothing new. We've been doing it all along. And the sample values are independent. Sample size is no more than 5% of the population size. Okay, so the bottom part of this kind of precursor we've been dealing with for a while, so that should be quite handy to you to figure that out, or to know that that's our first step in any kind of statistical analysis. So first, let's look at the classical approach. We determine the null and alternative hypotheses. I'm not even going to touch on this hardly at all because this is what we already know, okay? But here, since we're looking at a difference, I guess I should go a little bit more into detail. The hypothesis can be structured in one of three ways. We know this: two-tailed, left-tailed, right-tailed, where mu sub d is the population mean. It's the mean difference of the matched pairs, okay? So it'll be easier to see in an example in a minute. So our null hypothesis is that the difference between the means is equal, etc. Our two-tailed, of course, is that they're not equal. Our left-tailed is that the mean is less than our sample, our test statistic or mean sample, our mu sub naught or mean statistic, sorry, mean parameter. And then the right-tailed is, of course, the the population mean difference is greater than our data point. Okay. Step 2, we select the level of significance, 1 minus alpha, confidence interval, you know this. Step 3, we compute the test statistic, t sub naught, which then follows the student's t-distribution with n minus 1 degrees of freedom. And here we have a calculation for this t sub naught, where you have d bar, which is the mean, and s sub d is the standard deviation of the differenced data. Okay, again, I think that'll become a little more clear as we do the first example. And then we use table 7 to determine the critical value. Remember, for two-tailed, this is plus or minus t sub alpha over 2, right? Because this is, we have to include both of those areas to the left and to the right, because it's on the endpoints. The left tail is negative t sub alpha, and then the right tail is just t sub alpha. And remember that table 7 is a table for right-tailed values, and so that's why we use negative t sub alpha, etc. Okay, and then also t sub alpha over 2 for the two-tailed. I think it's a little more clear when you look at this. But then we look at our test statistic T sub naught, and then compare it with the critical value, which is either plus or minus T sub alpha over 2, or positive or negative T sub alpha, as you can see in all of these places. And we reject if the T sub naught value, our test statistic, is in any of these critical regions, depending upon which type of test we are doing. And then, of course, we state the conclusion at the very end. Okay, so this should seem pretty familiar. You need to know this formula for the test statistic of the differences, but the rest of this should kind of follow along as you're going through. Okay. If we now look at the p-value approach, all of the initial setup is the same until we get into the middle of step 3. So again, we're determining the hypotheses, the level of significance. We've calculated the test statistic in the same way, based on n-1 degrees of freedom. The d bar and the s sub d are both the same. There are values of the difference data. But here now we're going to use table 7 to approximate the p-value. And again, remember that if we have a two-tailed hypotheses, then it's the sum of both areas plus or minus T sub naught. We've typically done this as 2 times the positive value because that's the value that shows up in table 7. If we look at the value of T sub naught is the value to the left of the test statistic. But remember, if you have a left-tailed test, then the value in the table is going to give you this right-tailed test value, right? So if we want this, it's 1 minus whatever that T sub 0 value is in table 7, because specifically table 7 again gives you areas in the right tail or areas to the right of the T sub naught. And that's part of the reason why we also do 2 times. For a two-tailed test, we do 2 times the area to the right, or the p-value that we find in that table, because we know that these are symmetrical. In a p-value test, remember we compare the p-value that we find in our analysis to the alpha value, or the level of significance, and if the p-value is less than alpha, we reject the null hypotheses, and then of course we state the conclusion. These procedures are robust. This simply means that minor departures from normality will not adversely affect the results. However, as we've seen before, if you have outliers, you cannot use, or you should not use this procedure. So let's look at an example, and I think this will help point out the differences from what we've done before, and so it's not really that big of a stretch. Professor Andy Neal measured the time in seconds required to catch a falling meter stick for 12 randomly selected students' dominant hand and their non-dominant hand. Professor Neal wants to know if the reaction time in an individual's dominant hand is less than the reaction time in his or her non-dominant hand. The idea here is, you're right-handed or left-handed. They drop basically a meter stick or a yardstick, and they want to see how long it takes you to catch it. The thought is if you're right-handed, that you'll be quicker with your right hand than your left, and that's his hypothesis, that the dominant hand, he wants to find out if the dominant hand has less reaction time than the non-dominant. So you catch it quicker, meaning the reaction time is less, okay? A coin flip is used to determine whether reaction time is measured using the dominant or non-dominant hand first. This is a great addition in this problem that we often kind of overlook, and this is why we oftentimes have to repeat statistical studies, because we forget something like this. Maybe a secondary catch, maybe you've learned something or you're anticipating more, or maybe, so the order that you use which hand may affect the result. So kind of thinking through what might be some other things that impact the data before you even start can be very helpful. So here they made it double random by flipping a coin to determine if you're going to use your right or your dominant or non-dominant hand when you do the experiment, or whenever the student comes up does the experiment. And we're going to conduct the test at the alpha equals 0.05 level of significance. So here's the first difference. So we have all of the data. For example, here's student 1 in the first row. Their dominant hand, it took 0.177 seconds, and their non-dominant hand took 0.179 seconds. And so this is what we're calculating is the difference between these two values. Now, why are they dependent, right? Well, in order to have the second data point, you have to determine which hand is dominant, and that leaves the non-dominant hand. So you can see that this data points are indeed dependent upon each other, that it's a matched pair of data. So we simply subtract dominant minus non-dominant in this last column. So this has all of the differences in it. Here we've labeled the dominant data points as x sub 1, the non-dominants as y sub 1, and we simply subtract all those values there. Here we sum up that last table. Why do we do that? Because we also want the average or the difference mean. It's part of what we use to calculate the test statistic. Okay. We expect these numbers to be negative, right? Because we expect the dominant hand, your stronger, the hand you rely on more, to be quicker than the non-dominant, so the time is shorter. So if we take a shorter time minus a longer time, then it would be negative. And so we expect the differences to be negative. So basically we're trying to determine if the average, the mean of the difference, is less than 0. It should be negative. If we go ahead and calculate the average or the mean of the differences, negative 0.158 divided by 12, how many students tests we did, gives us a mean of negative 0.0132. If we then look at the standard deviation from the mean for all these points, we get a value of 0.0164. So you don't need to calculate that. I've gone ahead and, well, this is an example from the book. I did all the work. Okay. So of course, the first thing we need to do is verify the data comes from a population that is approximately normal and ensure that there are no outliers. The figure shows here the normal probability plot to the left and a box plot of the difference data to the right, where we can see there are no outliers. The correlation between the difference data, this is the plot of the difference, and expected z-scores is 0.978. Now correlation is simply the average product of all the pairs of z-scores. So we'd look at the x sub 1 z-score, the y sub 1 z-score, multiply them, x sub 2 times y sub 2 z-scores, multiply them, add them all up, and divide by 12 the number of test cases we had, students we had, and then you get the average product. And that's what that 0.978 is. If we look into table 6, which is the critical values for a normal probability test. Remember, this is where we use the sample size, and this is n equals 12. If you look at that in table 6, you'll find that the critical value is 0.928. And because 0.978, our correlation, is greater than our critical value, we conclude it's reasonable to conclude the data comes from a population that is normally distributed. Okay. So we can move forward. First, we're going to do this same problem both with the classical and p-value approach. So we did say that we wanted the difference to be less than 0 or negative. So for our null hypothesis, we say that the difference is equal to 0. That would mean that the difference is that the time is the same for your dominant and non-dominant hand. But Professor Neal, I believe, believes that the dominant hand should be quicker or stronger, and so the way we're doing the difference, dominant minus non-dominant, this would result in a negative number. Your stronger hand minus your weaker hand, your shorter time minus a longer time would give you a negative value, and so it's less than 0. Remember, the null hypothesis is always an equation, and then we have two-tailed, not equal, left-tailed, less than, and which is what this is, and then of course right-tailed would be greater than that value. The level of significance, we already saw that. It was given in the problem of 0.05. And so we compute the test statistic. Again, we use the mean divided by the standard deviation divided by the square root of the sample size. And doing that calculation, we get negative 2.788. Here what we do is we use table 7 to find the critical value based upon alpha equals 0.05. And of course our degrees of freedom, which is 1 less than the sample size, is 11. And if you do that and go down to the entry, you will see that our critical value is negative 1.796. Now when you look in the table, you're not going to see a negative value there, okay? But you've got to remember that the table is based on areas in the right tail. Because the distribution is normalized or symmetrical, the left-tailed would be that negative value. And so that's why we put that negative t sub naught for a left-tailed test as I went through the exercises. Okay. Here then we compare the test statistic with our critical value, and if the test statistic is in the critical region, or in this case because it's a left-tailed test, if the test statistic is less than our critical value, we would reject the null. In this case, it's easier visually to see it, but it's really important because you're not always going to have these tables or these graphs, etc. So remember what we're saying here is if our data point, if our test statistic is less than the critical value, when we use less than because it's the left-tailed test. So if our test statistic is less than the critical value, then we reject the null hypothesis. And of course we state that the sample data provides sufficient evidence at an alpha equals 0.05 level of significance to conclude that the reaction time in the dominant hand is less than the reaction time in the non-dominant hand. And again, we don't ever verbally reject the null. What we do is we state it in regards to what we're looking for. And in this case, the dominant hand was quicker, which means it had a shorter reaction time. If we do this same exercise with p-value, notice that the first 3 steps are the same right up to calculating the test statistic. Okay. But here what we're going to do is we're going to use that same table, table 7, to find the p-value for that test statistic, okay? And so here again we have the test statistic of negative 2.788, which we saw before. And then again we have our degrees of freedom of 11. So what we're going to do here is we're going to use we're going to look for that test statistic value in table 7, and then the p-value will be the values at the top, which correspond conceptually to the alpha value, right? The probability, that alpha value is the level of significance, is based on a confidence interval, which is based on a concept of probability. It's probable it will happen, right? So what we can see here is that when we find the test statistic, and again, remember this table is about a right tail thing. So even though our test statistic is negative, we're really just looking for the positive value in this 11th row, right? Because our degrees of freedom equals 11. So our p-value is between 2.718 and 3.106. So that, I just think I said that wrong. Our test statistic is between these two values. So our p-value is between 0.005 and 0.01, as you can see here. And I've put them in numerical order. What we then do once we've established the p-value is we compare it to alpha, or the level of significance. And if the p-value is less than 0.0 or is less than alpha, we reject the null hypothesis. Since our p-value is less than 0.01, which is less than alpha, which is 0.05, we therefore reject the null hypothesis, just like we did before. And then we have the same statement of rejecting the null hypothesis by affirming that we have sufficient evidence to prove the alternative hypothesis. If we did use technology, in this case StatCrunch, we find the p-value here is 0.009, which falls between 0.01 and 0.005. So that falls within the range that we said before. And of course, 0.009 is less than 0.05. And so we get the same result. We reject the null hypothesis. Using the technology, we get a more precise p-value, but in our case, it worked out fine. I guess it would be confusing. I'm trying to think if that would actually happen if our p-value range included alpha in it. Then it could get a little bit hairy. Our final objective for section 11.2 is to construct and interpret confidence intervals for the population mean difference of matched paired data. A 1 minus alpha times 100% confidence interval for U sub d, or the mean difference, is given by the lower bound is d bar minus t sub alpha over 2 times s sub d over the square root of n, and the upper bound is that same formula, but instead of a difference, we have addition or a sum. Okay. The critical value t alpha over t is determined using n minus 1 degrees of freedom, and d bar and s sub d are the mean and standard deviation of the difference data, as we've seen in the previous examples. The interval is exact when the population is normally distributed and approximately correct for non-normal populations, provided that the sample size n is large, which we've seen again and again. It's a pretty standard kind of operation. So if we look back at the data from the last table, using that data from our table, we're going to construct a 95% confidence interval estimate of the mean difference mu sub d. In the first step, we already did this, and that's to compute the difference data and also to verify the data is normalized or an approximate normal distribution. We also calculated d bar, which is the mean of all the data, the difference data here, 0.158 divided by 12. And we also computed, the standard deviation of the difference data. So we're ahead of the game here. So since alpha equals 0.05, right, we have a 95% confidence interval, then the alpha is that percentage left to 100% or 5% or 0.05. And our n minus 1, or our degrees of freedom, is 11. So if we go to table 11 and go to the 0.05 column and go to the 11th row, we will find the value for T sub alpha over 2, which is 2.201. Using this, we can now calculate our upper and lower bounds. As you can see here, we get negative 0.0236 and negative 0.0028. You can also do this with technology, of course, StatCrunch, or this example here is using the TI-84 calculator, and you can see that we get the same values for our d-bar, our standard deviation, and roughly the same for our upper and lower bounds. Okay. Based upon this confidence interval, we are 95% confidence, right? That's what we built, a 95% confident interval. The mean difference between dominant and non-dominant hands reaction time is between negative 0.0236 and negative 0.0028 seconds. Very technical. It sometimes is difficult to understand. But notice what this is saying is that we are 95% confident the dominant hand has a mean reaction time that is somewhere between 0.0028 and 0.0236 seconds faster than the non-dominant hand. And so that the middle phrase is much easier to understand. And of course, because the confidence interval does not contain 0, that would mean that they were the same, which is the null hypothesis. The evidence suggests that the reaction time of a person's dominant hand is different than the reaction time of the non-dominant hand. Okay? So that's the end of section 11.2.